our speaker is Hiroshi Hirai from the University of Tokyo.
Can you hear me?
Yes.
Yeah. Okay. So let me start the talk. So first, I would like to thank the organizer for giving me the opportunity to talk about my work on the related geodesically convex optimization. Okay, so this talk is about new algorithm for NC rank, which is also based on geodesically convex optimization, but this is not optimization on manifold. So this is a geodesically convex optimization on non-manifold space. So this work is joint work with Masaki Hamada. So let me. Screen cannot move. I'm sorry. Okay, so let me first introduce Edmond problem. Edmond problem asks to compute the rank of matrix A, including variables x1, x2, xm, where each coefficient matrix n by n matrices over field K. And the matrix A is considered as a matrix over polynomial ring and also considered in rational function field. So therefore, we can define the rank of matrix in this field. This problem of computing the rank of symbolic rank of matrix A can be solved in randomly polynomial time by substituting actual variables to each actual values to each variables xi. Then we can compute the rank by Gaussian elimination over a field K. But it is known whether this problem is in P or NP hard or NP complete. This is one of major open problem in theoretical computer science. And also this problem is related to many fundamental problems in diverse areas, such as combinatorial optimization and rigidity theory. For example, combinatorial optimization, so bipartite matching or more general matching problem can be formulated as a rank computation of special type of matrix A. So I'm a researcher. I was a researcher in a combinatorial optimization. So therefore, I'm interested in this problem. So recently, Ivanos et al. Introduced a non-commutative version of Edmond problem. Here, variables xi non-commutative. So matrix A is regarded as a matrix over a non-commutative ring. So in this case, there is a skew field of fraction of this ring, but there are many skew field of fraction of this ring. So, but there is a most generic field, which is called free skew field. So then the rank of matrix A in this setting is defined in this field. So this idea broadened the literature and leads to the breakthrough. So this problem is related non-commutative algebra and invariant theory. For example, null membership problem of this action is equivalent to singularity, NC singularity of this matrix. So, so handling elements in free skew field is quite difficult, but surprisingly, NC rank can be computed in polynomial time. So they showed that NC rank can be computed in polynomial time for if the field K is a complex field. So algorithm is based on operator scaling. So operator, it turned out that operator scaling is can be viewed as alternating minimization for geodesically convex function on the space of positive semi-defined positive defined matrices. So this function is not convex in ordinary sense, but in the Riemannian metric in this space, this function is geodesically convex along geodesic. Then NC non-singularity is equivalent to this optimization problem is bounded. So this is this work is a breakthrough, and so now this idea is generalized to more general framework of non-commutative optimization by Burgess et al., including Michael Walter and Paul Franks and others. So also Ivanus et al. Solved this problem for arbitrary field. So this algorithm is also interesting, which is based on one sequence. So one sequence can be viewed as a vector space generalization of well-known augmenting path algorithm for bipartite matching. So and this algorithm also uses a new idea of matrix completion by non-commutative algebra. So sorry. Main result of our work is to give conceptually different polynomial time algorithm to compute NC rank. So our algorithm is based on the combination of submodular function optimization on modular lattice and geodesically convex optimization on non-manifold cat-zero space. So submodular function is a discrete analog of convex function in combinatorial optimization. And cat-zero space is a metric space of non-positive curvature. So this space is also cat0 space, but our optimization is on non-manifold cat0 space. And we also introduce a new reduction technique of NC rank computation over rationals, which avoid bit complexity issue. So, this reduction use periodic variation to reduce the problem, the NC rank computation over finite field. So, this is also regarded as discrete convex optimization, another type of modular lattice, which is equivalent structure of Euclidean building. Okay. First, I mentioned submodularity in NC rank. So this theorem characterizes NC rank. So NC rank is equal to 2 times n minus this optimization problem, optimal value of this optimization problem. So variables, non-singular matrices, and so so variables are non-singular matrices P and Q with properties that PAKQ has zero block simultaneously in same position. Objective value is the size of this zero block. Okay. So NC rank is given by this formula. In fact, this optimization problem can be viewed as submodular function optimization on modular lattice. First, let me explain this. Let me explain coordinate-free formulation of this problem. So this problem is equivalent to optimization over vector subspace in this way. Okay, so here matrix AK is built as bilinear form over K. Okay, then variables, vector subspace, a pair of vector subspace such that each bilinear form vanish on the product of x times y. Okay, so this condition is equivalent to zero block condition, and objective function is a sum of dimension, which is equal to size of zero block. Okay, so then this condition, this vanishing condition, is included as a penalty term in objective function. Here, penalty parameter C can be taken as 2 times n plus 1 because dimension function is bounded by n. Okay. Also, family of vector subspace become modular lattice. So therefore, the problem can be formulated as optimization of modular lattice of vector subspace. Then this objective function is a submodular function in this sense. Here, L star is a opposite lattice, which is obtained by reversing partial order. Namely, this is a lattice of all vector subspace with with respect to reverse inclusion order. Okay. This is a lattice with respect to inclusion order. Then objective function satisfy this inequality. Here, if we take join and join and meet as this way, then this function satisfy submodular inequality. So I forget to explain the meaning of this term. So if the restriction of bilinear form to x time y has is 0, then rank is 0. Okay, this condition represent 0 block condition. Okay, so if this 0 block condition is violated, then this term is at least 1. Therefore, from this, we can see this problem is equivalent. Okay. So, so our approach to solve NC rank is based on this formulation. Then, so our algorithm is inspired by classical submodular function minimization by Robas, Gretcher, and Schreiber. So this is a classical submodular function. Then the submodular function is extended to convex function in Euclidean space by Robas extension. Therefore, minimizing this function is equivalent to minimizing this Euclidean convex function. So therefore, we can apply Euclidean convex optimization algorithm such as ellipsoid method. So our algorithm are inspired by this scenario. So, but for the case of submodular function minimization on modular lattice, there is no such nice convex Euclidean convex relaxation. But recent work shows that modular lattice can be relaxed to some cat-zero space. This is a continuous relaxation of modular lattice. Then submodular function can be extended to geodesically convex function on this cat-zero space. So this is a extension of this. In a sense, this generalizes a classical Robas extension theorem. Then minimize the Robas extension by some optimization algorithm on cat-zero space. Okay, this is a approach of our algorithm to solve this submodular function minimization. So let me introduce cat-zero space. So cat-zero space is a geodesic metric space such that every triangle is not thicker than triangle in Euclidean space. Consider 3-point x, y, z, and consider geodesic connecting them. Okay, so this is a geodesic triangle in this space. Then we can consider corresponding point in Euclidean plane, x bar, y bar, z bar, such that they realize distance, original distance in as a L2 distance. Okay, so this so so distance between x bar y bar is equal to original distance in space K. Okay, such x bar y bar z bar are determined up to uniquely determined up to rotation and reflection. Okay, so consider a point PQ in geodesic. Then we can consider a corresponding point P bar Q bar. Then cat0 inequality says distance in original space is at most corresponding distance in Euclidean plane. So this inequality represent geodesic triangle is slimmer than corresponding triangle in Euclidean plane. Okay, so cat0 space, the geodesic metric space is set is called cat0 if every triple of points and geodesic connecting them satisfy this inequality. Okay, so so example Euclidean space and hyperbolic space and more generally symmetric space of non-compact type. They are manifold, but cat0 space include non-manifold space. Also, so in the literature, complete cat0 space is more natural and appropriate. So such space is called Adamar space. So okay, they are Adamar space that is manifold. So such manifold is Adamar manifold. So this is a definition of cat0 space. So recently, so there are some interesting work on algorithm and optimization on cat0 space. So so important factor is that cat0 space is uniquely geodesic. Namely, there is a unique geodesic connecting any point. So therefore, we can naturally define convex function. The convex function is a function such that it is convex along the unique geodesic. So therefore, it is natural idea to develop convex optimization theory or related algorithm. So one of origin is the space of phylogenetic tree. In this work, they construct the space of phylogenetic tree as a cat0 space. So then there is a unique geodesic between two phylogenetic tree. So therefore, we can consider a midpoint of two different phylogenetic tree. This will be useful for phylogenetic analysis. Also, this work shows that certain robot give rise to a cat-zero space as it's a configuration of motion. Then, geodesic in this space corresponds to motion planning of robots. Then, by this unique geodesic property, computation of the geodesic is a natural problem. So such problem is a continuous shortest path problem. So for general case, continuous shortest path problem is NP hard. But interestingly, for some cat-zero space, there is a polynomial time algorithm to compute geodesic. So ON showed that polynomial time algorithm to compute geodesic in a space of phylogenetic tree. More generally, Hayashi, who is my PhD student, shows that geodesic in cat-zero cubical complex can be computed in polynomial time. With respect to some error. So cat-zero cubical complex is a cat-zero space obtained by gluing Euclidean cube. So Bachak also develop a proximal point algorithm for convex optimization cat-zero space. This is also natural direction of research. And cat-zero space sometimes obtained from some combinatorial object. For example, cat-zero cubical complex is obtained by filling Euclidean cube to each cube subgraph in median graph. So this is a median graph is a generalization of three or product of three and distributive lattice or something, some other class of graph. Also, poset and lattice sometimes gives cat-zero complex. So for in our algorithm, proximal point algorithm, and the construction of cat-zero space from poset or lattice important. Okay, which explained in the next slide. Okay, so let me explain ortho-scheme complex, which was introduced in the literature of geometric group theory. So let M be a graded poset. Consider the set of all convex, formal convex combination of a chain, okay, pairwise comparable element. So this is a geometric realization of order complex of poset. So order complex is a well-known concept in combinatorics. So next we define metric on this space. Namely, this is a simplex. So then this simplex is metrized by being a special Euclidean simplex in this way. Okay, so this is a simplex corresponding to chain. Then this simplex is mapped Euclidean simplex in this form. Okay, so bottom element is mapped to origin, and next element is 1, 0, 0, and next element is 1, 1, 0, and top element is 1, 1, 1. So also scheme is a convex hull of this point. So this is not a regular simplex, but is sometimes called standard simplex. Okay. So this is an example. Okay, this is a graded poset. For this chain, we consider a two-dimensional ortho scheme, which is a right triangle. For this chain, we consider three-dimensional ortho scheme. For this chain, we have this one. Then we obtain ortho scheme complex of this poset, which is a union of triangle and half of Euclidean three-dimensional cube. Then we can consider length. We can define length of path between x and y in ortho scheme complex KL, because each segment of this path can be measured in Euclidean metric in this simplex. Okay, so each segment belongs to some Euclidean triangle. Therefore, the length of path is well defined. Then we can consider metric. So which is defined as infimum over infimum of length over all paths connecting x and y. Then resulting metric space is a geodesic metric space. Geodesic means that every pair of points have shortest path that attain infimum of this quantity. So this inf is minimum for every xy. So there's a question raised in the geometric group theory, which is a class of poset having cat0 ortho scheme complex. This problem is is closely related to some important open problem in group theory. Yes, some poset has a cat0 ortho scheme complex, but some poset has an ortho scheme complex that is not cat0. So Boolean lattice is a typical example giving cat0 ortho scheme complex, which is isometric to Euclidean cube. This result is generalized to distributive lattice. So distributive lattice can be represented by poset by a Barkov representation theorem. Then corresponding ortho scheme complex is isometric to the order polytope of the poset representing distributive lattice. Then, since ortho scheme complex is realized as convex polytope in Euclidean space, so it is cathedral space. So this result is further generalized to modular lattice. So modular lattice as a cat0 ortho scheme complex. This is an example. But the important point is that corresponding ortho scheme complex is not realized in Euclidean space. Okay, so this is a modular lattice of all vector subspace of two-dimensional space. Bottom element correspond to zero space, and these points correspond to one-dimensional vector subspace. The top element corresponds to a whole space. Each chain we consider a right triangle. Okay, so ortho scheme complex obtained by gluing infinite many triangle along a longer edge. Moreover, consider a function defined on modular lattice. Then we can consider a piecewise linear extension defined on cathedral space. Okay, so if we are given a function defined on this point, then we can define a continuous function defined on union of triangle. So, for example, this point is a piecewise linear extension of vertices of function value on vertices. Therefore, from a discrete function defined on modular lattice, then we obtain a continuous function on cathedral space. So this theorem says that if the discrete function defined on modular lattice is submodular, if and only if corresponding piecewise linear extension is convex. Okay, so this generalizes classical robust extension theorem. Suppose if function f defined on Boolean lattice, then corresponding piecewise linear extension is defined on Euclidean cube. So this function coincides with classical robust extension. This is a generalization of the robust extension to modular lattice. But the space is no longer Euclidean space. Okay, so let me back to the problem of NC rank. So this is our problem for NC rank, okay, which is a submodular minimization on the pair of modular lattice, which is a pair product of modular lattice, which is also modular lattice. Then by robust extension, then the problem is convex optimization on cathedral space. Okay, but currently we have no powerful method, powerful optimization method on cathedral space, such as ellipsoid method. So we utilize a special form of special property of objective function, which is a sum of relatively easier convex function. Then we apply splitting proximal point algorithm developed by Bakak. So here K is a complete cathedral space, Adamar space. F1, F2, Fm are convex function on K. the goal is minimize sum of these convex functions. So this formulation can be applied to our problem. So they are convex functions. So splitting proximal point algorithm is to iterate this update. Zk is a current point. Next point is minimizer of one of fk plus some distance from current point. Okay, so k is taken modulo m cyclically. Okay, so this is a strict convex function. Therefore, minimizer is uniquely determined. Okay, so then so he showed that this algorithm converges to optimal solution under mild assumption. So this result is generalized by Otta Parfia. They proved that if each Fi is ellipsis and F is strongly convex and lambda k is taken as this one, then they showed this convergence result, sublinear convergence result. Okay, so our algorithm use this result in time complexity analysis. Okay, so our algorithm apply splitting proximal point algorithm to this objective here in this setting. Okay. But to guarantee strong convexity, we add some perturbation term, but this is a minor detail. So after polynomial iteration, then we have a solution sufficiently close to optimal, because Lipschitz constant of this function is bounded by polynomial of m and n, because c is 2 times n plus 1, and rank n is bounded by n, and the dimension function is also bounded by n. Therefore, Lipschitz constant is bounded by polynomial of n and m. Also, diameter is also bounded. Also, we can choose suitable epsilon. Therefore, polynomial iteration, we have such a solution. Here, f has integer value. Therefore, optimal solution exists in the support of this solution. Recall that solution is a convex combination of a chain of vector subspace. The optimum exists in the summand of this sum. Okay. So this is a outline of algorithm. So our main technical contribution is splitting proximal point algorithm is actually implementable in polynomial time. This means that each update can be done in polynomial time. Okay, so we need to solve this problem as a sub-problem. which is still non-trivial problem. Okay, so problem is optimization of all convex combination of a chain of vector subspace. Therefore, this problem is still non-trivial. So the proof is based on lattice theoretic argument. Optimal solution exists in the apartment, which is a subcomplex of Boolean lattice generated by a current point. This is current point, and orthogonal complement. So this is a convex combination of chain of vector subspace, and this is a convex combination of orthogonal complements of with respect to bilinear form xi, and vector subspace in the support. Then these vector subspace generate Boolean sublattice. Recall that the orthoscheme complex of Boolean lattice is cube. Therefore, in this apartment, so the problem is usual convex optimization problem, Euclidean convex optimization problem, which is easy convex quadratic problem, which can be solved exactly. So, okay, so there's no time, I skip. So this explains lattice theoretic lemma behind this argument. So in a complemented modular lattice, for any two chain, there is a Boolean sublattice B, including them. So here, complemented modular lattice is a product of lattice of, essentially product of lattice of vector subspace. And also there is a nice retroaction from whole lattice to Boolean sublattice. This gives retroaction. This induces retroaction from orthoscheme complex to orthoscheme complex of Boolean sublattice, which is equivalent to Euclidean cube. So this is essentially a axiom of a building. So it is known that complemented modular lattice is equivalent to spherical building type A. So I explain some good point and bad point in our algorithm. Our algorithm is conceptually simple, I think, described uniformly in arbitrary field. So I hope there is an application to other problem. But point is the speed. This algorithm is polynomial time, but very slow. So because of less use of characteristic of objective function. Also, currently, optimization theory in Katsura space is less developed. So we used a very primitive algorithm to minimize our convex function. Also, a more serious problem is bit complexity. So our algorithm consists of polynomial number of vector space operation, intersection and sum, but which cause exponential bit explosion of base, explaining base representing this vector space. So therefore, naive application of our algorithm cause exponential bit explosion, unfortunately. So I introduce a new idea, resolve this issue, which is a reduction of our problem, NC singularity over rational to that over finite field, GFP, by using a periodic reduction, periodic variation. So recall this is a definition of periodic variation. A and B are prime to P. Then we consider this problem. So variables non-singular metrics such that periodic variation of each entry of PAKQ is non-negative. So each entry cannot be divided by negative power of P. The objective is a sum of variation of determinant. Then we can show.
Sorry for the interruption. You have like 9 minutes left, so
okay.
Yeah.
Okay, so I finish soon later. Okay, then NC singularity is equivalent to this optimization problem is bounded. Also, if bounded, then the optimal value is bounded by polynomial of input size. Here we use relation between periodic variation and bit size of integer. So this is the case of p equal to 2. So this is a two-adic variation, but bit size is larger than this one. So by using this fact, we reduce polynomial number of NC rank computation over GFQ. So okay, so I skip details. So this is a detail of outline of algorithm. So we can consider a periodic expansion of PAKQ. Then each coefficient matrix is a matrix over GFP. Then we can consider NC rank computation, NC rank of symbolic matrix defined by leading matrix over GFP. Then we can consider zero block, whole block. We can update P and Q to decrease objective value. Okay, this is an outline of our algorithm. So this is regarded as discrete convex function, discrete convex optimization on another building structure. Okay, skip. So finally, let me discuss possibility of our approach to apply other related problem. So PQ scalability of matrix positive operator defined by to probe matrices by triangular matrix is determined by solving this optimization problem. Also, plus complete separation. So finiteness of plus complete constant for PL data is determined by solving this optimization problem. So these objectives are sum of supermodular function. Therefore, this is a minimization of the submodular function over this modular lattice. So therefore, our approach is applicable, but it gives pseudo-polynomial complexity because Lipschitz constant dependent on exponentially on bit size of parameter p. Therefore, it has difficulty. Also, I don't know whether a periodic approach can work. So I consider a more general problem of non-competitive optimization. let G be a connected reductive algebraic group over complex number. And consider the representation. Then null membership problem is equivalent to the problem of asking whether origin belong to the closure of orbit. So this problem is equivalent to the boundedness of this problem. Okay, here K is much more compact and the norm is K invariant. Then this problem is a geodesically convex optimization problem over a symmetric space of non-positive conversion. So recently I found that so checking unboundedness, so boundedness, not this problem, the only checking boundedness is reduced to geodesically convex optimization on another Cattell space obtained from the boundary of this space at infinity. So boundedness is an asymptotic property. Therefore, this is characterized by asymptotic behavior of this property. So boundary of a symmetric space has also certain structure, certain metric. It is known that the boundary of a symmetric space is a spherical building. Then from this, we obtain a Euclidean building, which is also Cattell space. For example, boundary of GL modulo UN is essentially a weighted sum of flag. So this space is essentially also scheme complex of modular lattice of all vector subspace. Therefore, in the case of GL modulo in the case of GL, then this problem is optimization of this space, then which is essentially same as also scheme complex of modular lattice of vector subspace. So this is why optimization problem over such vector subspace appear in this context. But I don't know whether our approach is actually applicable. So there are many difficulties to be overcome. Okay, so that's all. Thank you for attention. So.
Thanks a lot for the talk. Are there any questions?
Thanks. Yeah, I was wondering about the connection of this continuous algorithm to the geodesic convex algorithm for the same problem. And I guess you didn't mention it, but the SLN times SLN acts on the lattice of subspaces, and therefore it acts on the continuous space, the Lovász extension you construct. So it's actually a representation also. So you could potentially run the alternate minimization algorithm on your space, it seems. Is there any relation between what you would get if you do this to what your algorithm does?
So your question is a relation between alternating minimization and the
original algorithm, the alternate minimization, and this algorithm.
So original algorithm work on this space essentially. but our algorithm is built as an algorithm on the boundary of this space. Okay, so boundary is in general is not manifold. So therefore, I think so it is different. For example, consider the case of metric scaling. Okay, so scalability can be determined by network flow problem. Okay, but to obtain actual scaling, we have to solve continuous smooth optimization problem on Euclidean space. Okay, so our algorithm solve analog of network flow type problem. Okay, so usually the case of metric scaling, we need decide existence of scaling. Then existence can be checked by some network flow or matching type problem. So our algorithm solve this kind of problem. So which is essentially checking boundedness of this problem. So therefore, I think our algorithm is different from alternating minimization approach of this objective function.
You mentioned there was some convergence analysis for the proximal point methods,
Mm-hmm.
and it required some extra conditions, right? Smoothness and strong convexity and stuff.
Mm-hmm.
Could you give some idea of where those come from in this problem?
Mm-hmm. Sorry?
Could you give some idea of where these extra conditions come from in the problem? Like, why do you have Lipschitz and strong convexity and stuff?
So your question is about the condition? So sorry, I'm not sure for your question. So
like you applied this convergence analysis to your particular problem, right?
Mm-hmm.
With your particular sum of functions.
Mm-hmm.
So like, why in your case are your functions strongly convex in Lipschitz, and like why is this fast?
So sorry, so this object function is very special. So and bounded Lipschitz constant and some. So your question is a proof of this result, no? Or
just some intuition for like why it works.
Intuition. Okay, but the proof is essentially same as a Euclidean case. So the proof is based on so there's a Euclidean version of splitting proximal point algorithm. Then they showed this result by modifying the proof of Euclidean case. So it's the answer that satisfies you.
It looks like, okay, we are 5 minutes over, so I think we should stop. So thanks again, Hiroshi. And then it's lunch break now. So I think the next talk is at 2 p.m.